Okay, in this video we're going to talk about yet another method for solving differential equations. This one only applies to linear equations. Of course, we'll talk about what linear equations are. Sounds funny saying linear equations when we're talking about differential equations, but you'll explain in a minute. So, a differential equation is linear if it can be written in the form dy dt is equal to a of t y plus b of t. Where A and B are arbitrary functions of t. Again, the emphasis here being that y is the dependent variable, and in this case t is the independent variable. So when we think of linear functions, it's really kind of like you'd normally think of a linear function. We're just treating the expressions involving t kind of like constants. So you can see that this does sort of take the form of dy dt equals my plus b, right? You can see that the b is the kind of like, well, that's not the case here, but and the slope is kind of like that. So that's why they call them linear differential equations, because they look kind of like a normal linear equation that we're used to. So here's an example of one. Dy dt is equal to t squared y plus cosine t. So you can see that in this case your a of t would be equal to t squared, and your b of t would be equal to cosine t. So just to be clear on what we mean by a of b and a of t and b of t. Sometimes they'll come in non-explicit form. So like, for example, if I had dy dt is equal to, minus 3y is equal to t times y plus 2. So that would be implicit because the independent and dependent variable are mixed in together. But of course we can rewrite this as dy dt is equal to t plus 3 times y plus 2. So if I add 3y to both sides and factor out the y. So again, in this case, you could see that a of t would be equal to t plus 3. And b of t in this case would be just a simple constant. So again, the key to this is the dependent variable is linear. Meaning if it has y squared or y cubed or cosine y or e to the y, none of those would be considered linear differential equations. Okay, so we have two types of linear equations. We have the homogeneous, and of course the non-homogeneous. And how do you tell them apart? In homogeneous, b of t is equal to 0, and non-homogeneous, b of t is not equal to 0. So the homogeneous ones, of course, are a little bit simpler because they're separable. They're guaranteed to be separable. If they're non-homogeneous, then some are separable and some are not. So if they're homogeneous, then we can solve them using the method we learned earlier of separation of variables. So because hopefully that, I don't know, I'm assuming that's obvious. So because if you have a function, I mean a differential equation in this form, then we can easily separate the t and the y from each other by going dy over y is equal to a of t dt. And so they're separable. Okay. And I guess maybe likewise, if I have dy dt is equal to a of t y plus b of t, so that plus is going to cause a problem because there's no way to get the y out. If I divide both sides by y, then this becomes divided by y. It's possible that if I could factor the t's out, you might be able to leave just a y there. But anyway, these are not separable. Actually, I'm not thinking of a way where they would be, but these always will be separable. So these are the homogeneous are easy to solve. Well, we have a method for solving it, and the non-homogeneous we don't yet. So, but also linear differential equations are quite nifty because there are a lot of models that can be easily they can be modeled using a linear differential equation. And remember the basic principle for writing a differential equation to model something is we want to keep it simple. And linear differential equations are considered simple because we have a method for solving them. So so they come up a lot is the point. Okay, so let me talk about the linearity. Linearity principle. Okay, so if y sub h of t is a solution of the homogeneous linear equation, then any constant multiple is also a solution. K times y sub h of t. So if I know that if I have some function that I know is a solution to my homogeneous linear differential equation, then I know that I can multiply that same function by any constant and it'll still be a solution. Okay. Now again, this only applies to homogeneous equations. Okay. Now the second part, the extension of the linearity principle. Here we go. Let's see. Linearity principle extended. So let's say that y sub h of t is any solution of homogeneous equation, and y sub p of t is a solution, I guess it'd be a solution of the non-homogeneous equation. Then y sub h of t plus y sub p of t is also a solution. So just to be clear, when I say y of h of t is any solution of a homogeneous equation, or we could say the homogeneous part of a non-homogeneous equation. So in other words, if I have an equation that's dy dt, which is equal to a of t y plus b of t. So we're saying that this is a solution to just this part, and we're saying that this is the solution to a solution to the whole thing. Then we know that, let's say green, that this is also a solution to the whole thing. That's the idea. Okay? And likewise, suppose y sub p of t and y sub q of t are two solutions of the non-homogeneous equation. Then we know that y sub p of t minus y sub q of t is a solution of the homogeneous equation. Therefore, all that is to say that k of y sub h of t plus y sub p of t is the general solution of the non-homogeneous equation. So that is the linearity principle extended to deal with non-homogeneous solutions. So the basic idea is if we can come up with a solution, to the homogeneous part, if you will, or the a of t times y. If we can come up with a solution for that, which we should be able to because it's separable, and then we can come up with one solution for the whole equation, then we can add those two together to get the general solution. In other words, something that represents all solutions. Okay? So let's do an example now. See if that, of course, it always makes more sense once you do an example. So let's say, for example, we have dy dt is equal to cosine of t times y plus 1/5 times 1 minus t cosine t. Okay? So we'll start out by finding that k, the k times y sub h of t. So we're going to find the homogeneous solution. In other words, the solution to just this part. So we can do that by separation of variables, and we get dy over y is equal to cosine t dt. Integrate both sides and we get natural log of y is equal to, and that would be equal to, let's see, the integral cosine would be negative sine t plus c, which means y is equal to e to the negative sine t, the k out front. Okay? Whoops, that should be negative. Glad I cut that. So this is actually be y equals e to the sine t with the k out front. So that's that k times y sub h of t. So that's the solution to the homogeneous part of the equation. So this is a solution to the yellow part. So then the next step is if we can just come up with one solution for the whole equation. And in this case, I'm giving you one just so you can see how it works. We can, let's say that, y of t equals t over 5. So I'm suggesting that that is a solution to the non-homogeneous equation. And let's check to make sure that's true. So if we take dy dt is equal to cosine of t times y plus 1/5 times 1 minus t cosine t. Okay? So we're going to replace y with t over 5 with an equals t over 5. It looks like it's a negative. Okay? So, first of all, the derivative of t over 5, right, would be just 1/5. Okay, so the derivative of t over 5 would just be 1/5. And so then the question is that equal to, and of course, in this case, y is t over 5, so that would be t over 5 times cosine of t plus, and we distribute that 1/5 through, we get 1/5 minus t over 5 cosine t. And notice that the t over 5 cosine t minus t over cosine t would be 0, and so we end up with 1/5 equals 1/5. So sure enough, this t over 5, surprise, surprise, is a solution to the entire differential equation. It's a solution. So what the linearity principle tells me is that therefore the solution y of t equals k times e to the sine of t plus t over 5 is a solution, is the general solution for that non-homogeneous differential equation. So this came from, so if we liken this back onto the thing up here, so that part, right, we already said is the yellow part, and then this part down here is that part, the one particular solution of the non-homogeneous equation, and we added the two together to get the general solution. Okay, let me do another example. Well, let me sum up. So how do we do this? This one was obviously just given to us, and we didn't come up with that t over 5. It was something that I gave to you already. So here's the procedure. There's a 3-step procedure for this. So the first step is find general solution of the homogeneous part of the equation. aka, or otherwise known as the a of t. Oops. So we're just, first step is to find the solution to this equation. And we do that by separation of variables and integrating both sides, okay? Second step is find one particular solution for the non-homogeneous. Or the whole equation. So the dy dt equal to a of t times y plus b of t. So we have to come up with a particular solution for the entire equation. First one, we just look at just the part involving y. The second part, we try to come up with one particular solution that works for the whole thing. And then finally, third step is, this of course is the hard step, put a star by it. Third step is obtain general solution by adding what you got from step 1 and step 2. Okay? That's the process that we're going to go through. So let's try one. So dy dt is equal to negative 2y plus e to the t. Okay? So negative 2y is, that's, our negative 2 is the a of t, and e to the t is the b of t, right? So you can see that. You can grab a different color up here and just put this little, remember, we're thinking about this form. Right, so you can see the negative 2 is the a of t and e to the t is the b of t. So first step is we're going to find the solution to just this part. We're going to ignore the e of t, e to the t for a moment. Okay, so we're going to separate variables, so we're going to get dy over y is equal to negative 2 dt, and of course that's, if we integrate both sides, we're going to get natural log of y is equal to negative 2t plus c. Then we exponentiate both sides and we get absolute value of y is equal to e to the negative 2t plus e, or times e to the c, which we could just change that to a constant out front. Okay. And now that it's a exponential equation, k could be negative or positive, so we don't need the absolute value anymore, so we end up with y equals e to the negative 2k. Okay? You good so far? So that was my y, my k times y sub h of t. That's the solution to my homogeneous part of my non-homogeneous equation. So now we move on to step 2. This is the difficult part, like I said. And essentially what we're going to do in this part for now is we're just going to guess. We're going to take a guess, hopefully not a wild guess, but a guess. What is a solution that might work here? Okay? So we look at the equation. dy dt is equal to negative 2y plus e to the t. And we know that we're going to be taking the derivative of something, and it's essentially going to be close to itself plus some other e to the t added to it. So that, of course, makes us think of e to the t. So what if we just go for the kind of the simplest step, or the simplest guess, and say, because we really are kind of guessing here. So let's just say, what if y of t was just e to the t? Would it work? So then we're going to try it. So we're going to take dy dt. The derivative of that, of course, is just e to the t. And that would be equal to negative 2 times e to the t plus e to the t. Okay? So did it work? Well, it looks like we were so close because we end up with e to the t on this side, and negative 2 times e to the t plus 1 times e to the t ends up with a negative e to the t. And so stinking close. So we know we're on the right track. In fact, our suspicion is that we could probably, this would work if we just have the right coefficient out front here. And this is the way this usually works, is there's a clear indication of what type of function we might want to use, and then we have to adjust it based on the right coefficient. So what we're going to do instead now, just to give ourselves a little bit of wiggle room, is we're going to take, I'll leave that alone, take a second guess, but this time we're going to say, let's let y of t equal some constant times e to the t. That way we have some wiggle room and we're all done. Okay? So then once again, if we go d, we'll take a derivative. This is my little, sorry, I did put my little p into there. We're going to take the derivative of that with respect to t, and this should be y of p plus e to t. So we're going to check that and see if it works. So of course the derivative of that is still just alpha e to the t, and this is going to be negative 2 alpha e to the t plus e to the t. So now we actually have some what I call wiggle room, because we can adjust the alpha so that this actually works. So in this case I have alpha e to the t, and over here I have so then we add these two together and we get what? Negative 2 alpha plus 1 times e to the t. And so what we really have here is, what we need to have is, we need alpha to be equal to negative 2 alpha plus 1. So we can easily solve that by adding 2 alpha to both sides, and we get 3 alpha is equal to 1. Therefore alpha must be equal to 1/3. Okay, so then we go back to our original guess and look what it was. Our original guess was alpha e to the t. So now our new guess, a particular solution to the non-homogeneous equation, is 1/3 e to the t. And you can check that and make sure it works. So now we've got to come up with our general solution. So our general solution is y of t is going to be equal to the solution to my the homogeneous part, which was k times e to the negative 2t, k times e to the negative 2t, plus the one particular non-homogeneous solution, which would be plus 1/3 e to the t. So that is the general solution to that differential equation. I think I'll do one more example here. Yep, this one's going kind of long, but okay, so that's dy dt is equal to, we'll do one that's not explicit, plus 2y, which is equal to cosine 3t. Okay, first of all, we want to come up with the solution for the homogeneous part. So that would be, we just want to find out what dy, solution for dy dt equals. We can move the negative 2y, or the 2y to the other side, so it'd be negative 2y. So we end up with dy over y, which is equal to negative 2 dt, which means natural log of y is equal to negative 2t plus c, and that gives me y is equal to k times e to the negative 2t. Looks familiar. And I say that jokingly because the one we just did had the same one, but also because this is can happen every time if we're just solving something involving t times y. So this type of equation, dy dt equals a of t y. If it's just a y there, it's always going to end up being dy over y, which equals a of t dt, and that's always going to end up being natural log of y equals a of t times t plus c. And so this form is going to show up a bunch. You buy that? Okay. So that's my solution to the non-homogeneous part. Now we need to come up with a particular solution for the whole thing. So y sub p of t. And we want something that'll fit that. Okay? So now here's the interesting thing. Because there's a cosine here, my first thought might be to just make something involving cosine. But then if you think about it all, if you take the derivative of cosine, it's going to produce a sine. So what we really need is something involving cosine and sine. So, and also learning from last time that putting that little alpha in there helped. So here's a guess, not a wild guess, an educated guess. We're going to say, what if this, let's go with alpha cosine 3t plus beta sine 3t. Again, why I'm guessing sine and cosine together is because I know that if it was just cosine and I took the derivative of it, it would produce a sine, and I'd be in trouble. Because if it only had cosines, this would be cosine, that would be cosine, and that would be a sine, and there's no way you can get them to equal each other. So we're going to guess something involving sine and cosine, and we put the alpha and beta out front to give us some wiggle room. Okay? So now we're going to try our guess. So of course this is going to be the derivative of y sub p dt. We'll just leave it in explicit form. Plus 2 times y sub p is equal to cosine 3t. So let's fill that in. So the derivative of that would be negative 3 alpha sine 3t plus 3 beta cosine 3t. So that's that part. And then plus 2 times that up there, so that'd be 2 alpha cosine 3t plus 2 beta sine 3t. And that would be that part. And finally, that would be equal to cosine 3t. So now we're going to add together what we can and see if we can make this work out. So negative 3 alpha sine 3t and 2 beta sine 3t. So that would be negative 3 alpha plus 2 beta times sine of 3t plus 3 beta plus 2 alpha cosine of 3t. And that's supposed to be equal to cosine of 3t. So now we need, in order for this to work out, we need negative 3 alpha plus 2 beta to be equal to 0, don't we? Because there's no signs over here. And we also need 3, I'll put this in different order, 2 alpha plus 3 beta. We need that to be equal to 1, so that it'll end up being just cosine of 3t. So you remember back in Algebra 1, solving a system of linear equations, it shouldn't be too bad. So I like the elimination method, I'd probably multiply the top one by 2, the bottom by 3. That gives me negative 6 alpha plus 4 beta equals 0, and 6 alpha plus 9 beta is equal to 3. Add them together and I get 13 beta is equal to 3, which means beta is equal to 3 over 13. Nifty. So then if I plug that in over here, I get negative 3 alpha plus 2 times 3 over 13, 6 over 13 is equal to 0. Okay, so let's, so that means that negative 3 alpha is equal to negative 6 over 13. If I divide both sides by negative 3, I get alpha is equal to 2 over 13. So, if I remember what our original guess was, it was alpha cosine. So that would be 2/13 cosine 3t. And the beta was sine, right? So that would be plus 3/13 sine 3t. So that's the particular solution of the non-homogeneous differential equation. So then we just need to add to that our solution to the homogeneous part, the general solution to the homogeneous part. So that's k times e to the negative 2t. So we put over here k times e to the negative 2t. And that would be the general solution to the non-homogeneous differential equation. And again, you could check that, plug it back in, make sure that it works, but it does. Okay, so I think that'll do it. Got a couple examples to go on, and there is a worksheet to practice this a little bit.